welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. This time again, remember, this is not always the case because sometimes we discuss things with European researchers in our new series, but this time it is Luxembourg, which also means that we are proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. Now that I'm done with all the typical introductions, we have an atypical introduction because, of course, a new guest is here with us, and the guest is Timon Schild, who is a mechanical engineer, former ESA graduate trainee, and currently PhD student at the European Space Resources Innovation Center, ESRIC, for those of you who know, where he conducts research about lunar resources utilization. Timon, thank you so much for coming today.
Thanks for having me.
So we have utilization and resources already, so we are starting with the first term, which is ISRU or ISRU, right, that we talk about a lot in the space community. But ISRU is a little bit more than what you're specializing in, because you're specializing only in lunar resources. Am I right?
Yes. So ESRIC in general, we look mostly at resources on the moon, but there are, of course, also other resources in the field. People are talking about Mars or asteroids, but most of the work we're conducting so far is the moon because it's the closest to us, both timeline-wise and distance-wise.
Exactly. But for those who don't know, ISRU is what?
Yes, so ISRU or ISRU, it's In Situ Resource Utilization. It's sometimes a field also called space resources. Basically, we're looking at natural resources that are in space, so outside of Earth. As I said, the moon, Mars, asteroids. And we want to see how we could use them, not necessarily to bring it back to Earth, but to kind of improve what exploration missions in the future could do. So if we want to explore the moon in depth, we need to have construction materials on the moon. We need to be able to find oxygen, water, etc. And so we don't have to bring all the supplies from Earth. We want to be able to find them where we are in space.
We are recording just straight after one of the Takeoff episodes. I don't know if you know Takeoff, the Science Challenge show here in Luxembourg.
Actually, I don't.
Okay, so I'll tell you about it later on, and this is a shame. You should definitely watch it. And the one that was really there on Sunday was about space and space exploration. And what it is about, for those of you who don't know, really, please watch it. It's a brilliant show where you have youngsters competing against each other in science challenges. And as I said, space was the topic. And I just loved it because one of the challenges they had, there was a rover that they had to maneuver around on an exoplanet, theoretical exoplanet, of course. And, you know, it was a kind of a computer-generated thing that they had to move around. And then there were different lakes there. And they had to figure out which one contains water, right? Okay, we are not talking about the delay and all this stuff that normally, you know, that would not work with, you know, joysticks for exoplanet. Let's forget it. But simulation was great. And at a certain moment, one of the groups said like, oh, look, this lake seems to contain diamonds. We're going to be rich. And I just loved, there was a specialist there as well from iSpace, Philippe Ludwig, who said like, yeah, but you need to bring it back first, right? And I just love this kind of, you know, Earth-centric thinking that we have, of course. But as you said, what is important here is that we are mainly looking at resources that we want to reuse in situ, where we are, not bringing them back.
Yes, and also on that, it's actually a very good point. What's valuable on the moon is not what would be valuable on Earth. I mean, oxygen on Earth is something that's all around us, so we don't really care about it. Whereas on the moon, it becomes one of the most precious resources because you need it to fuel your rockets, you need it to breathe. The same goes for water, etc. And I mean, in a way, oxygen would probably be more useful to have on the moon than diamonds.
Exactly. That's a very good point. So just listeners, do check this episode out and all the other ones because it's a brilliant show that you should watch. But just coming back to our focus now, so space resources as such. Very often in the field, if it's a journalist writing about it, we talk about, you know, mining, right? And we're trying to avoid that word.
I personally wouldn't necessarily avoid it because there is definitely some stuff from the mining industry that will be useful to us because what we want to do in the end, if we're taking about any useful scale of operation, will be to some extent inspired by mining, what we do on Earth. It has a negative connotation because of, for example, environmental aspects on Earth. One reason not to use mining is because often it associates what we do with bringing it back to Earth. And as I said, that's not what we're doing. But otherwise, actually, getting inspired from the mining industry is something we are looking into.
Listeners, if you're more interested in the field, remember this year, as usual, there'll be the Space Resources Week in Luxembourg, where you can learn more about the field. And I love this kind of discussions between the mining industry and the space resources field, because it's kind of slowly trying, but it's very difficult, right? Because the mining industry is an established industry, but still trying to understand what is going on and trying to exchange and trying to find the common language, because that's a problem. I remember at the Space Week last year, there was one person talking about the fact that it's just like we don't speak the same language or whatever else.
Yes, that's very true, actually. There's a difference of scale. I mean, currently for a lot of our processes, we're working in the lab. So we talk about grams, kilograms of material, whereas the mining industry will only start worrying about something if you have multiple tons of it. Also, a lot of the processes in the mining on Earth use, for example, a lot of water, which will be something we won't have on the moon. There are some differences, but I think it's really important to talk with each other and find a way to integrate what they know into what we do. Exactly.
Or, the discussion with the pharmaceutical industry for space exploration as well, that is hopefully ongoing, stronger, and interesting for both sides. Should be interesting. Okay, we diverted a little bit. So when we talked space resources, you defined them a little bit, but I just still want to be more precise. So space resources, right now we're focusing on oxygen, and oxygen is one of the resources. We have water. What else?
It's very broad. As I said, it's all the natural resources that are in space and not on Earth. So
natural. So, for example, debris flying around, is that a space resource or not? I know you're not a specialist in that.
No, that's actually a very good point. There are people actually at ESRIC also looking at that, at recycling derelict spacecrafts, for example, as a space resource. So yeah, we can include that in the broadest definition. I mean, some other things, we could also include sunlight. So a lot of our satellites are actually, in a way, already using space resources because they're using the sunlight to power their batteries. Another really important thing, and that's kind of what I'm working on, is more the minerals, the rocks, and also the metals contained in those minerals. So that's more kind of construction materials or manufacturing materials. And then there's also some rarer, smaller things. We call them usually volatiles. So on the moon, stuff that would be in gas form and that we want to capture. It could be ammonia, it could be sulfur-based gases, etc., etc. But kind of the three main points, I would say, currently are construction materials, oxygen, which is a really important one, and water for the moon. Yeah.
On the topic of diamonds, I need to mention that as well. You didn't talk about rare earths. So that's...
Yes.
We have to say this, another elephant out of the room.
I mean, there are rare earths on the moon. We call them creep. So it's potassium, K, rare earth elements, and phosphorus. They are present on the moon. The question there is the concentration. We actually had a chat about that yesterday at the office. Is yes, they are there, but you also have similar concentrations of them on Earth. So why would you mine them on the moon if you can find them on Earth? Another kind of elephant in the room that's often mentioned is helium-3.
Exactly, I was waiting for that too.
Yes, so helium-3, for those who don't know, it's an isotope of helium that can be found on the moon, so as a gas kind of trapped in the lunar ground. And theoretically, it can be used, for example, for nuclear fusion in kind of a different process than the deuterium-tritium fusion reaction, kind of conventional fusion reaction, if there's something like a conventional fusion reaction. So it can be found on the moon. The question again is the concentration. I mean, we're talking parts per billion. So, okay, you could get some, but you will need to process tons and tons of lunar material to get a usable amount and then bring it to Earth. I'm not saying it's impossible. I'm saying for now it's quite a long shot. So it's not going to happen in the next 10 years or so, where we will maybe start already looking into the oxygen, into the water, etc.
So let's focus on the shorter shots, if we can call them like that. So in your case, you're looking at the Lunar Regolith.
Yes.
Right? That's what you're interested in. Okay, once again, for those of you who don't know, maybe I hope you do know because you listened to my interview with Catherine Hadler, but if you don't, what is Lunar Regolith?
Regolith is a scientific term basically to talk about all the loose rocks and rock fragments that cover a celestial body. So you could talk about regolith on Earth, actually, or on Mars, or on the moon. So on the moon, the lunar regolith, as I said, is all the rocks. It goes from large boulders all the way to very fine dust that basically cover the whole surface of the moon. I mean, if you've ever seen images from Apollo astronauts on the moon, there's this kind of gray sand-like substance covering everything. So that's what we call the lunar regolith.
So it's not just dust. Because I noticed that there's a tendency to say, okay, lunar regolith, lunar dust, or lunar regolith, lunar soil.
Yes, so the regolith is kind of the all-encompassing term. I mean, if you have a huge boulder of 10 meters across on the moon, it's still a loose rock fragment on the lunar surface, so technically it's still regolith. But most of the time, when we talk about lunar regolith, we will talk about kind of the finer fraction, so less than 1 centimeter. The rest, we would say it's just lunar rocks. So it's really this sand-like stuff. And then you have lunar dust, which will often refer to the very fine fraction. So maybe less than let's say, 0.1 millimeter or something like that, which is kind of the really nasty stuff that gets everywhere, that sticks to your clothes, to your spacecraft, etc., etc. Lunar soil is also a term that's used kind of interchangeably with lunar regolith. And again, it just refers to this kind of top layer of the moon. I personally don't like lunar soil too much because soil sounds like biological matter like you have on Earth, but it's used in the literature, yeah.
Yeah, you can't go on and plant something in there right now.
Not directly. There is some work in using it as a substrate to grow plants, but you will need to add the biological matter, which you don't find on the moon. All the carbon and nitrates you will need to source somehow.
So what is there in the regolith? What do we know?
As I said, the regolith is basically fragments of rocks. And maybe to begin with, we can wonder a bit about where it comes from. So basically it comes from millions and even billions of years of meteorites impacting the moon. So if you imagine that the moon originally had a solid crust, which it still has, well, basically after millions of years of bombardment with meteorites, well, you start breaking up this crust into finer and finer and finer fragments. And so basically nowadays, the whole moon is covered by 3 to maybe 20 meters of those rock fragments. So basically they're rocks that have the same composition than the crust of the moon underneath, which isn't so different.
Just a question. The same composition. Are we sure? I mean, these are the meteorites that we're hitting. Didn't they leave something behind as well?
So the meteorites mix into it as well. And also you can have, if you have large impacts, I mean, they disseminate the ejecta all across the surface. So you can have kind of soil fragments that traveled from a very long way on the moon, but kind of the bulk will be tied to what the local composition of the underlying bedrock is.
So we're talking concentration again, right? The concentration is higher when it comes to what is there from the moon.
Yeah, and somewhat interestingly, those very large impacts, you can also use them to date regolith. Because when you look, for examples, at glaciers on Earth, where you have those layers where you can see some geological events like volcanic eruptions, you can do the same on the moon. You can kind of date a certain depth of regolith where you see ejecta that's characteristic from one large impact that you know of.
So yes, I interrupted you. So you started telling me that it's mainly what the moon had, and with the different meteorites that it was being hit, it became this more dusty fragment.
Yes.
And what is inside?
So exactly. So when you look at the regolith, say on a microscope, you will find rock fragments. So as I said, just rocks that have been broken down. You will also find glass fragments, because with this impact, you had melting of the minerals. And so it's glass fragment like obsidian, like volcanic glass. You also find some particles that actually can only be found on the moon, or at least can't be found on Earth, which are called agglutinates, which are basically small particles of rock that have been molten together by the force of the impact. So the rocks in themselves are not super interesting compared to Earth. I mean, it's broadly speaking compositions that you also find on Earth. So a lot of silicates, basalts, etc., etc. It's more.
I would say that the rock experts would get offended by this. So the rocks are not so interesting. Yeah, but
not more interesting than the ones on
the
Earth.
Yes,
Exactly.
I get it.
But also, what is really interesting is the form factor. So this powder that can be very fine, and also that is very sharp, because you don't have any erosion, you don't have any atmosphere on the moon, You don't have any water on the moon, or at least water in liquid form. So basically the sharp edges that come from the rocks breaking stay sharp. And that's actually a big problem for when we want to send astronauts and equipment there. Is this regolith is super abrasive for everything we will send there. So that's actually something we need to take into account.
You said when you look at it under the microscope, but it doesn't mean that we can all do that, right? You don't have, infinite amount of regolith that you don't have it in your lab, do you?
No, we don't have it in our lab. There is a very limited amount of it. So we have about, I think it's 380 kilograms of lunar rocks that have been brought back, mainly by the Apollo missions. You also had the Luna missions from the Soviets that brought back some grams. More recently, you have the Chang'e missions from China. So yeah, we have a very limited stock of it. If you have a great idea of what you want to do with it, you can actually ask NASA if they want to provide you with some samples to analyze. So that is something that is feasible if you have an interesting analysis to do with it. But most of the time, especially for what we are doing when we look into the processing of this regolith, when we want to look into processing multiple hundreds of grams or kilograms of it, we can't just use the real stuff. Yeah.
So what do you do?
So in that case, what we work with a lot in our lab, or almost exclusively in our lab, is lunar regolith simulants. So it's rocks from Earth that we selected based on their composition, again, because we know we find the same rocks on the Earth and on Moon. So we select the same rocks here from Earth, we grind them up to the same kind of size distribution that we expect on the Moon. And then we use that kind of as a cheap replica of the actual stuff that comes from the Moon.
So it means you are creating the simulants yourself? You don't buy them on the market?
We're actually buying it on the market. There's a few companies that are specialized in this. Depending on what you want to look at, maybe you want to investigate a very specific mineral that is present in the regolith, then you can, of course, just take that mineral and do it yourself. There's quite a lot of projects depending on what you're looking at that are doing this. But in our case, most of the time we're using commercially supplied ones because also they're the most established ones. And it also allows us to compare what we're doing with what other people are doing if we use the same kind of substrate.
I don't know whether in science 300 kilograms is enough of a sampling. How sure are you that the simulants are actually really similar to lunar regolith?
First of all, it depends on the simulant. There are different simulants for different things. You have simulants that are there just to have a large volume of them. Not too far from us in Cologne, they recently opened the Luna facility, which is, I'm going to offend a few people, but a really big sandbox. It's like 700 square meters, where they basically replicated a lunar environment to train their astronauts, to test out some systems, etc. There, obviously, what you want is a lot of simulants. So they sourced, from what I know, relatively locally from quarries, material that is still can be considered a regular simulant. It's mostly basaltic. But there, for example, if you want to do a very precise chemical process or something like that, you probably will not choose that because that was mostly selected just for the volume. Then you have other simulants where kind of the chemistry of it has been tailored to better match the composition of regolith or the composition of a certain area of the Moon. So it really depends what you want to do with it. And then there are a few things that are very difficult to replicate. For example, those agglutinates. There are some simulants that have kind of artificial agglutinates, but it's not done by the same process. So again, there are differences there. And the microstructure I was talking about, this kind of very sharp-edged microstructure, is quite difficult to replicate. So most of the regular simulant we would use just for their composition won't replicate those things. But it's still a very useful tool. You just need to be aware of the limitations of it.
Of course, definitely. And there are a few other limitations also on the Moon. And one of it is actually the subject of your pub quiz question today, right? So as usual, listeners, remember now is the time that Timon will ask the quiz question and the answer only at the end of the podcast.
The question I wanted to ask to the listener is, do you know what distance we, as the humanity, have traveled on the lunar surface up to date? And also more specifically, what distance was traveled actually by humans and what distance was traveled by automated systems like rovers?
Okay, great. So remember, answer only at the end of the podcast. This distance by rovers, I guess it keeps increasing, right? Because we keep having missions. somehow.
Yes, and we actually have at least one that I'm aware of, rovers currently active on the moon, currently moving forwards, and there are a few others planned. One of them is actually built in Luxembourg.
Yes.
So the rover from iSpace that I think is currently on its way to the moon and
as
should
far as I know,
hopefully
yes,
be there soon and increase that distance by a bit.
Exactly. So remember, this answer will not be valid forever, but just for as of beginning of February that we're speaking, that is correct. Okay, good. So I have a feeling I know a little bit more now about the simulants, about the regolith and whatever, but what is your interest in it?
What we at ESRIC and myself are looking at are what we can extract from it. Currently, I'm looking at the oxygen we can extract from it and the metals we can extract from it. There, maybe you may be asking yourself, oxygen on the moon? I thought there was no atmosphere, nothing. Well, actually, if you look at rocks and minerals, even on Earth, they actually contain a surprising amount of oxygen. If you take quartz, a very abundant mineral through a lot of the rocks we have here on Earth, it's basically a crystal of silicon dioxide. So 2/3 of the atoms in there are oxygen atoms. And if you add this all up together, well, Lunar Regolith, so the rocks you find on the moon, they contain 40 to 45% of their weight in oxygen atoms. You just need to get them out of there. So that's the kind of technologies we're looking at ESRIC.
Just need to get out. I think it's not just. So what have you managed so far, and what is the technology you're using?
Yes, so there are a few different technologies that are being investigated. What I'm working on, it's called molten salt electrolysis. So it's an electrochemical process. You may be familiar with the electrolysis of water that we do on Earth to produce hydrogen. What you do is you take water, H2O, apply a potential to it, an electrical potential, and basically the electrical energy will split H2O into H2 on one side, your hydrogen, and O2, the oxygen. So basically we want to do the same thing with the Lunar Regolith, with the minerals that are in there. To do this, we need higher potentials, and so we need something that's more stable than water to do it in, so we use molten salts. It could be table salt. You could actually do it with table salt, so sodium chloride. What we are using is calcium chloride, which is just a different flavor of table salt, let's say. It's still salty. So
you've tried, I assume.
It's actually used in the food industry to replace sodium chloride. Anyway, so calcium chloride, you can melt it to at 950 degrees. Then you have a bath of this salt. And then basically you put your regolith into it. And by applying a potential between the regolith and another electrode, you're going to start breaking, for example, those silicon oxygen bonds or calcium oxygen bonds or aluminium oxygen bonds. And you get the oxygen out of it. Currently, we have been running experiments using 20 to 30 grams of Lunar Regolith simulant, and it showed that it actually works quite well. So using this technique, you can get more than 95% of the oxygen present in the Lunar Regolith simulants out of it in the form of gas. So it's actually one of the techniques that works best in terms of how much of the oxygen you can get out, but it's still difficult to implement like all the other processes. So what we're looking at now is how can we scale it up to a more meaningful scale to actually produce some usable amounts of oxygen.
So scaling up means just more molten salt.
Exactly. So we should get in the coming months kind of a next generation reactor that instead of working with tens of grams, we will start working with kilograms of material. And then in the coming years, we're planning to scale that up even further to work with like hundreds of kilograms.
Well, one of the problems, with technologies on the moon and other planets is that for this particular thing, you obviously have to bring the salt to do that, right? Yes,
exactly. And that's actually a very important point for a lot of the processes is how much consumable do you need to bring? And it's really a key point because, well, if you need 100 kilograms of salt to produce 100 kilograms of oxygen, you just bring the oxygen. So in the case of molten salt electrolysis, you can almost see the molten salt like the frying oil you would have at your local fast food. It's something you can technically reuse and reuse and reuse to produce multiple batches of French fries, or in that case, of oxygen. But like the frying oil, you will always have a bit of losses. You will have some of the salt that will stick to the solids you're taking out of it. You may have a little bit of evaporation. You may have some contamination. So that's actually one of the key metrics that we're going to investigate with this new system is how much of the salt, how good can we reuse the salt from batch to batch to batch. Because even if we have, let's say, 2-3% of loss from batch to batch, it already jeopardizes the whole thing, because if you need to replenish that, you may as well just bring oxygen from the ground.
Okay, but you're not only getting oxygen, you're also getting some metals. So maybe it will still be worth it.
Yes, exactly. And that's actually the specific topic I've been looking at, is because this molten salt electrolysis technology is so good at getting all the oxygen out, what you're left over at the end in terms of solids, so we call it the reduced regolith because you've electrochemically reduced it, it's basically all the metals that were originally bound to the oxygen. So in there you will have the silicon, you will have calcium, aluminium, iron, titanium, depending again on kind of what area of the moon you are in. But they're all mixed together in a very complicated way. So what I've been looking at now is, well, first of all, what form do they take in those solids? And then how could we separate them and refine them to a point where we could use them, for example, as a construction material? Could you somehow produce an aluminium alloy out of this stuff? Because although currently it's a byproduct from the process, we're really interested in the oxygen, it's still some material that we put a lot of energy into. So we don't want to waste it, especially in such a scarce environment like the moon. So we're looking at ways to make use of this material.
So you said they are bound in a very complicated way. Does it mean it's different than on Earth? Or what's the problem here? How do you normally separate such metals?
Normally on Earth, if you want to produce metals, what you would do is you would refine the metal oxide before putting it in any form of process. So for example, if you want to produce aluminium, you first want to have very pure aluminium oxide, and then you put that through a process, which actually is also a molten salt electrolysis process, to get the oxygen out and obtain your very pure aluminium. Here, because we're more interested in the oxygen, we're kind of turning it on its head. And so because there's oxygen bound with all kinds of different metals, well, we just throw everything into the reactor. So which is good because we get all the oxygen we can get out of it, and we don't need to sort too much through the regolith beforehand. But then you're left over with a mess of a metal, which is basically an alloy of all the different things you find in there. So that's actually a question that is worth asking in this study is there an optimum? Do we want to waste a bit more time up front to isolate some specific minerals, but then maybe it actually works better in the process because some minerals seems to work better than others. And then also it may be easier to split the metals afterwards.
One more thing, I mean, this reactor, you have it here, just not far away from the media center, not on the moon. So how probable is it that the same technology we could actually use on the moon? Or you're right now only trying to figure out how much oxygen you can get out?
Yeah, so we kind of know how much oxygen we can get out. It's more under what conditions. And again, how much salt are we losing in the process? How much we're destroying our equipment in the process, because it is a very aggressive process. But bringing that to a payload level that could be sent on the moon is a really interesting challenge because, well, that's a process initially that comes from the metallurgy industry on Earth. So they didn't really care about the mass or the size of things as long as the materials were relatively cheap. For example, they're running with a lot of salt compared to the amount of metals they're producing. For us, if we need to bring a lot of salt, well, it's going to make our spacecraft very heavy. So we need to work on all of those aspects. But there are actually some studies already in progress to send a first demonstration mission of this process to the moon, which would only be kind of a one-shot. So pick up a little bit of regolith and demonstrate it 1, 2, or 3 cycles to show that we can produce some amount of oxygen on the moon. But of course, that's only the first step. Then we'll need to look into how can we scale up the process and make it viable for the moon. And that's going to be investigated with kind of our next generation of reactors.
Or at a moment, someone finds out that there is so much water and ice on the moon that you will focus on that.
Yes, and that, I mean, part of our team is already focusing on that. So it's not my area of specialty, but water ice on the moon is definitely one of the most interesting resources. So for the people that don't know, again, you may wonder, why are we talking about water on the moon? We thought it was a dry piece of rock. Well, actually, if you go to the polar regions of the moon, you have something that's called permanently shadowed regions. So if you imagine a crater at the lunar South Pole or North Pole, this kind of divot in the ground, because the sun is basically shining horizontally at the pole, well, there's spaces in that crater that never see sunlight. So it's extremely cold. And we know that this will trap all sorts of volatiles, different gases, or stuff that would usually be in the form of gas. And this actually includes water. So we know for a fact that there is some form of water in those regions. We know that from remote sensing data. What we don't know is the form that it has. And that is actually a very important and very interesting questions for the next steps of the exploration of the moon is, what does this water ice look like? Is it a layer of frost deposited on top of the lunar regolith? Is it a very tiny coating on individual grains? Or are there big blocks of ice that we can just grab and go? So that's actually something we don't know. And the remote sensing data isn't enough to tell us that. So we actually need to get there and know what's there. Because if we can't get water, then yes, producing oxygen, producing hydrogen becomes much easier. But there the challenge is actually, okay, how do we get to the water?
There's always a challenge. I mean, it's not so easy.
That's where the other processes that use lunar regolith, they're more challenging to implement. Like the process in itself is more complicated. But we really like the lunar regolith as a feedstock because that we have everywhere for a fact.
That is very true. So you don't need to make sure that the water is there and in what concentration. Today the key word is concentration, I think. Okay, good. You talked a lot about molten salt electrolysis, but there is more. I guess there are other methods. Maybe there's a better method than this.
Yes, I don't know about better, but there are other methods out there definitely, which are kind of at similar stages. So developed at lab scale. Some of them have already been scaled up. So we can split them in different categories. So if we stay in the world of electrolysis, there's something called molten regolith electrolysis. So basically to get rid of this problem of having to bring the salt as an electrolyte, the idea is, why don't we use the regolith directly as an electrolyte? So you melt the regolith, you basically produce lava, and then you electrolyze the lava directly. Sounds good because you don't need to bring the extra weight of the electrolyte and you don't need to manage the salt, etc. But you need much higher temperatures. And also the lava is a very viscous liquid that can be difficult to work with. But that's definitely one of the competing techniques, if we can call it that's worth investigating. And then there's another kind of category of techniques where you use gases to attack the regolith and get the oxygen out. One of them is hydrogen. So if you flow hydrogen through the regolith, and we actually also have a test reactor for that in our labs, well, the hydrogen is going to kind of latch onto the oxygen and you get water basically out at the other side, or H2O, and you deplete some of the oxygen present in the regolith. In some ways, that's kind of easier to implement because you're just flowing the gas through the regolith, but it's much less efficient on some minerals. So you can only get a certain amount of the oxygen out. You'll never get to the stage where you get with the electrolysis process where you actually remove almost all of the oxygen that's there. And then there are also a lot of other kind of exotic processes that looked at. One I kind of like on paper is called vacuum pyrolysis. So the idea is if you heat regolith to very high temperatures under vacuum, at some point the oxides are just going to start splitting by themselves and you're just going to start getting oxygen out. So you don't need any consumable. You only need the energy to heat it up. So on paper, it sounds really nice. The problem, again, is you need to work at very high temperatures for the oxides to dissociate. And once they do that, you end up with oxygen ions at very high temperatures that just want to attack all the materials that are around. So it's a very interesting process on paper, but it still needs to be matured and developed. The bottom line of all of this is, in my opinion, there are a few different processes that are being investigated, and I don't think there's one process that will match all the needs and that will cover everything, especially now that we don't really know what works on the moon. So I think all of those processes will, to some extent, have to be tried on the moon. Maybe one will win over all the others, but it's also very possible that you'll have different technologies present for quite a long time.
Okay, you're in the field, so you're the right person to address it to. How do you react when you have all these visionaries, or however you want to call them, talking about lunar bases, Mars bases, and whatever else? Is it going to happen in our lifetime or not?
The lunar base, I hope so, because that's my career plan. But
you want to move there? You mean? Or?
No, but to help building it.
Okay.
Before starting to talk about Mars or even further, I think the lunar base is a first necessary step. If we talk about exploration, that's actually why we want to do a lunar base in the first place, is because if we can show that we're able to do a lunar base, the moon being only, let's say, 3 days away, we'll never be able to do the same on Mars. So it's kind of a trial ground that we have to go through so that we can then go further into the solar system. Lunar bases, there are some more or less optimistic timelines out there, starting at the beginning with the big thing at the moment is the Artemis program, led by NASA, with also contributions from ESA and other space agencies to go back to the moon. The aim is to have humans back on the moon by 2027, I think is the current timeline. And the tail end of this Artemis program has always been presented as having a sustained presence on the moon. I think in the latest documents I read, there's no kind of specific date associated to that, but there are some dates elsewhere. For example, the moon base that the Chinese, together with the Russian and other space agencies, are pushing forward, they're aiming for 2035, for example, to have a first kind of basic lunar base that would then be developed into something bigger by 2045. So I think to answer your question, if and when we'll get a lunar base, I think we'll get a lunar base. We're not going to start building cities on the moon. When I talk about lunar base, it's more kind of like a research station that you have in Antarctica, for example, something of that scale. In terms of when, I think 2035 at the earliest, I would say more late 30s, early 40s would be kind of a reasonably optimistic timeline for that.
Yeah, we're going very much into the future. And of course, whenever we discuss space, there are always these skeptics that say, like, why bother with it? So what is your answer when you have like, why are you doing space exploration? You should be applying your knowledge to Earth.
I think it's a really fair point, actually. I mean, especially when you're in tough geopolitical climates or with all the concerns about environment, etc., etc. It is a valid concern. What I usually reply to that is that exploration in itself allows us to build technologies. So, for example, the molten salt electrolysis technology we're basically looking at how can we produce stuff in a very resource-limited environment. So how can we make the best use of the resources we have there? And this could be applied on Earth as well to produce, let's say, aluminium alloys from different kind of minerals that we haven't considered so far. So I think there's definitely the technology development argument, and just it gives a dream and a vision that allows us to develop the technologies further, and we don't know what technologies we'll find along the way.
Yes, exactly. But there's a long way to go. And the long way to go is also shown in the answer to the question that you actually prepared for us today. So once again, if you can remind us what the question was and then give us the answer.
Yes, so the question was, what distance has humanity traveled on the moon so far? And that had two sub-questions, is how much of this distance was actually done by humans and how much was done by rovers. Actually, so far, we've traveled about 145 kilometers on the lunar surface, which is already a quite impressive figure.
Actually. I was prompting it for it to be lower. So sorry, listeners, if I kind of made you think it's not that much. But yes, because I thought it was less.
It's already quite an impressive figure. But then again, putting it back in context, 145 kilometers here from Luxembourg, it will get you maybe to Namur in Belgium. The lunar surface, it's larger than the continent of Africa. So it's still a very small amount of the moon we have explored. And so of those 145 kilometers, you have 90 kilometers that were done by humans and 55 with rovers. Then again, they were only done in certain areas of the moon. For example, if you look at the far side, there's only been 2 missions to the far side, the Chinese mission. So there we have covered 1.5 kilometers. So that already brings it down a lot. And then the polar regions, there's not really anything. So those kind of permanently shadowed regions that could contain water ice, which would be so interesting to investigate from a scientific point of view and also from an ISRU point of view. Well, there we haven't traveled any kilometers in those really interesting areas. So there's still a lot to explore, both in terms of just exploration of the solar system and science and stuff to be learned from the moon. We can also learn a lot about Earth by going to the moon, and also a lot of technological development to do to help us going further into the solar system.
Yes, exactly. And this is a very nice way to finish our discussion today. And listeners, if this subject interests you, there is quite a collection of episodes about space where I discussed both space resources. Also, we talked a little bit about CubeSat and pocket cubes. There was a discussion about exoplanets recently, actually, with a professor from Austria. Very, very interesting one. I'm going to share all the links in the show notes. And keep listening to podcasts and listening to science podcasts. And thank you, Timon, so much for coming today.
Thanks for having me.
And this is it for today. As I said, keep listening, keep suggesting guests as well. Maybe you have some comments that you want to share, or maybe something you think that we should be discussing in this podcast. We are present on all the social media, all the major podcasting platforms. This was Silex, and my name is Hanna Siemaszko.